Welcome, Calculus AB. This is Lesson 2.9 continued, higher order derivatives, tangent line, and rate of change. Let's begin. So, continuing that previous lesson, we just did power rule. We learned about derivatives. Now we have higher order derivatives. So it's just the idea that you can just keep doing like a second derivative, or a third derivative, or a fourth derivative. You can keep doing more derivatives. So I might say, hey, find the second derivative of the function. Well, you just do it twice. And just this is the idea of what the notations look like. So we just went over this notation. First derivative, that's just normal derivative. But if you do a second derivative, so we just do y double prime, f double prime. This d squared y over dx squared is also second derivative notation. I don't use this as much, but you should be comfortable with this notation. Now, when your numbers get so big, we stop doing these tick marks. So sometimes you'll see textbooks do like y to a fourth right here. This is not like y to the fourth power, which gets really confusing. When I do in parentheses right here, it's implying fourth derivative. You might also see notation with Roman numerals just to differentiate. So yiv or f of iv means the fourth derivative. Sometimes you see that. So you might have to do higher order derivatives. So let's do an example. F of x is 1 over 2 times the cube root of x squared. Find f prime of 1, f double prime of 8. So first, to find f prime of 1, I have to find f prime of x. But before that, I want to rearrange this so I can actually solve it using power rules. So this is the same thing as 1 over 2 times x to the 2/3 power. And I want to move this to the top because for power rule, it's got to be on the top to make it work. So I'm going to rewrite that as x to the negative 2/3 over 2. Or you can even think of that as 1/2 times x to the negative 2/3 if you want to write it as a coefficient. All right? So f prime of x, I'm going to just write it out here. F prime of x is the derivative of this. So it'll be 1/2 times negative 2/3 times x to the negative 5/3. So cancel on the 2's. This comes out to negative 1/3 times x to the negative 5/3, and now we're going to plug a 1 into this. Well, the neat thing is when you plug, so f prime of 1 is going to be negative 1/3 times 1 to the negative 5/3. 1 to any power is just 1. So my answer is negative 1/3. That was very easy. Now I want to find double prime at negative 8. So I got to find the second derivative of x. So I'm going to take this function and derive this function. So derivative of that will be negative 1/3 times negative 5/3 x to the negative 8/3 when you subtract 1. Cleaning that up, that becomes positive 5/9 on the bottom times x to the negative 8/3. Now I got to plug in negative 8, which is kind of gross. But I'm going to rearrange this to a square root or a root function because it's easier for me to do the math. So 5/9 over x to the positive 8/3, which is going to be equivalent to 5 over 9 times the cube root of negative 8 to the 8th power. Yeah, because we're plugging in negative 8. Actually, so I don't even want to plug it in this. Actually, I don't want to deal with this. I want to deal with plugging it in right here. So we got 5 over 9 x to the 8/3. And so what you have to find, I want to do that on the side over here. This is kind of a weird thing. You don't do it too much. Negative 8 to the 8/3 power. So when you have a rational exponent, I want to root it first. So I'm going to go cube root of negative 8. Cube root of 8 is 2. Since we're negative 2. You can odd root a negative number. That's going to be 2. So now I do, or negative 2 to the 8th power from here. Well, it's an even root, so you're going to end up with a positive number. And 2 to the 8th power is 4 times 2 times 2, 4, 8, 16, 32, 64, 128, 256. It's 256. So your answer is 5 over 9 times 256. Oh, that's kind of big. But there you go. All right, let's do another one. Talk about equations of tangent lines. So this is another application. So we already mentioned that, and we have that playing. It's the slope of a line. Well, a line can be an equation of a form. So remember, there's y equals mx plus b. There's also another equation, y minus y1 equals m times x minus x1. This is where this is going to come back, especially point slope form. We might want to write the equation of one of these tangent lines. Well, I think we're going to use point-slope form. All you need is a point, x1, y1, and a slope. But we already learned our slope is the derivative at that point. So we're just using what we just learned to find the slope of an equation line, of an equation of a tangent line. Now, there's another note here. If we want to find a line perpendicular, we use something called the normal line. This looks like this. All that means is opposite reciprocal. Opposite reciprocal. So if your slope was 5/2, your opposite reciprocal would be -2/5. We went over that before. So find an equation of a line tangent, for example, to this graph at the point 1, 6. Well, 1 is your x1 and 6 is your y1. So we have those. I need to find my slope. To find my slope, I find my derivative. F prime of x is 20x to the 4th minus 6x. So to find the derivative at this point, that means plug in the 1 for the y. So your slope m is going to be f prime of 1, which will be 20 times 1 to the 4th minus 6 times 1. Order of operations, that's 20 minus 6 is 14. So my equation is going to be y minus 6 equals 14 times x minus 1. I can leave it like that. I'm done. Now, if I want to find an equation of the line normal to that curve, you have to take that slope and do opposite reciprocal. So your slope in this case is going to be -1/14. My answer is y minus 6 equals -1/14 over x minus 1. Not too bad. That doesn't come up too much, though, but it's there. All right, non-differentiability. So functions aren't necessarily have a derivative. That GIF that's going on, it's got a derivative everywhere. But sometimes you don't have a derivative. Where does it not exist? In these cases, where you're not continuous because of holes or jumps or asymptotes. We're also not continuous or not differentiable when we have something called a sharp turn. So that means because you got to think like limits case. You got like the limit, the slope over here is -1, and then it just immediately turns into +1. Like negative to positive. You need to have like a smooth curve with to be differentiable at a point. Just like limits, they have to like the limit or derivative as you're approaching both sides has to be the same. You also can't do vertical tangent line because basically the slope when you have vertical tangent line, your slope is like 1 divided by 0, undefined. So we say this is non-differentiable when you have a vertical tangent line or a slope of 1/0. So a note, so this kind of breaks it down too. A note here, if a function is not continuous, is not differentiable. So these are not continuous, therefore not differentiable. And a function may be continuous, but still not differentiable. These two are continuous, but you can't differentiate at those points. All right, so some examples, where is it not differentiable? Absolute value function is a function that has the V shape. Sharp turn right here. It is not differentiable at x equals 0 because of a sharp turn. Take this case. Now, when you have piecewise functions, in pretty much every case, you're not going to be differentiable where it changes. So we're going to say x equals 0. It's not differentiable. In this case, because it's going to also be a sharp turn. In this case right here, this is also not differentiable because you're going to have a jump right here if you graphed it. So at the handoffs on piecewise functions, those are not differentiable just most of the time. This case, so you're not differentiable where you're going to have a hole. In this case, look at the denominators. You're going to have a hole or an asymptote at x equals 0 and x equals 1. And in this case, so what's the graph of the cubed root of x look like? And I would graph it on a calculator just to prove it to yourself, but it looks something like this. And what happens is, and I don't think that was even good, but you have like this tangent line right here at 0. So we say it as x equals 0 because it's a horizontal or vertical tangent line. All right, rate of change. So another word for slope is rate of change. How much your rise over run, change of y over change of x. That's another word for slope, so it's basically another word for derivative in a way. So sometimes we might want to find like what we call an average rate of change. To find the average rate of change, it's just the slope between 2 points. So basically you're finding the slope of a line between 2 points. So you do not have to use the derivative of this, and you can use the equation y2 minus y1, x2 minus x1, your change of y over change of x. Now sometimes we want to find instantaneous, so you want to find the rate of change at a certain point. This means the derivative at that point. So find the derivative and then use calculus and then plug in that point. So let's see some examples. So if I had this equation, find the average rate of change from 10 to 30. So I got to find my 2 points. So I have an x and an x. These are like your x1 and x2, but I need to have corresponding y values. I like making an xy chart for that kind of stuff. So I'm going to do x is 10, x is 30. If x is 10, and you plug in 10 in your function, so f of 10, you're going to get 10 cubed plus 2 times 10. So that's going to be 100 plus 20, so 120. Now, if you plugged in 30, so f of 30, you're going to get 30 cubed plus 2 times 30. 30 cubed is going to be 1,000. I should have put another 0 here. Oh, I messed that up. Oops. Okay, so it's going to be 1,020. And if you plug in 30 cubed, that's going to be 9,000. Oh, not even that. It's going to be 27,000 plus 60. Why are these numbers big? 27, 60. Kind of gross. So the average rate of change between those 2 points is going to be the change in y over change in x. So I can just plug this in, 27,060 minus 1,020 over 30 minus 10. Okay, the bottom, that math is easy. It's 20. The top, that's going to be 26,040. And if you reduce this, you can cancel out the zeros. You can reduce everything by 2. So you're going to get 1,302 would be your final answer as the average rate of change. Pretty big. Now try this. Instantaneous, so I mean derivative at x equals 10. So that just found the average derivative. If you want to find the derivative at a certain point, we just have to find f prime of x, which is going to be 3x squared plus 2. And we want to find f prime of 10. So 3 times 10 squared plus 2, which is going to be 3 times 100 plus 2, which is 300 plus 2, or 302. That was easier. And that's it. Stopping right there.